myself, I suppose. I am working at McKesson Medical Imaging Group. I am currently the test lead for the performance group. Well, at McKesson, there is a lot of work. We do systems that X-rays, your CT scans that you take in the hospitals needs to be analyzed by radiologists. Doctors, they charge per exam. They examine the exams very quickly. It's considered that the X-ray exam, they examine it approximately in 15 seconds. What does mean that? That if they examine an exam in 15 seconds, if this exam, they charge by exam, the money, every exam that they get some dollars. And our performance is bad. If every exam in order to appear in the screen takes 15 seconds, they are going to screen to us. So performance is extremely important in our business. That is what I am doing, trying to analyze the performance. However, the most important thing is, if the performance is good or bad, why is good or bad? And here, this will be the focus of the talk today. However, before going to that, I am going to do some preliminaries. The agenda is mainly this. I want to insist that performance testing should be treated like a scientific experiment in which you are going to control some parameters and the others are going to be free. So we will review very quickly the scientific method without forgetting about errors, something that a lot of people forget about them, and well, the results are very fine. And then we will go to a little bit more to the meat very quickly, to put some notions about analyzing the data. As testers, there are a lot of testers in this room. What we can do as a tester? Well, we can be pass and fail. We can follow a script. We can compare the result with the requirements. If it doesn't match, fail the next one. Okay, this is a very valid way to do testing. However, we don't add a lot of value to this kind of testing. There is another kind of testing in which, in addition to that, we try to pinpoint to the developers or to the architects or to the other stakeholders where the problem is located. This is what I call it added value testing, and it's especially suitable to performance. To say the performance is bad, you say yes, where? Especially in very complex systems. So, as performance testers, we need to analyze the whole system. However, the first thing begins with hypothesis. A hypothesis is your guess, in plain work. You are going to have a system. The system is very complex, database tier, middle tier, business layer, network, hardware. You can say, okay, I guess, hopefully it's an educated guess, that my problems are going to lay in the database. Because when there are problems, the database always is the blueprint. Okay, this is fine. This is your hypothesis. Then the thing that you need to do is to start to create a test system, an experimental system if you want, in which you are going to control as many variables as possible in order to prove or disprove your thesis, your hypothesis. This realize that you can put the focus in very different areas. Your performance problems can be in all these different areas. The fact that the performance that comes from the database is bad doesn't mean that the network is going to be good. However, when you design your experiment, you focus in one area. You can focus in this example that I'm putting here in, I don't know, in the database, or you can focus on the network. Well, try to analyze which parameters you have. Try to fit them. Try to see if these parameters are dependent or independent. For example, in the case of the network, the utilization and latency are independent up to a certain level. When the utilization starts to be very high, the latency starts to be affected by the utilization. So depending how you design your experiment, these two parameters are going to be independent or are going to be dependent one from the other. So you need to be careful when you design the experiment. Again, we are focusing in this example with the network. We can make another example in which the database will be the subject of our attention. So this means, among other things, is that the network cannot become a bottleneck. So if you have the suspicion that the network, you have two bottlenecks, one the database, the other the network, you need to make sure that the second bottleneck is not going to kick in. Because if not, you are going to get results, but it will be very, very difficult to interpret. I'm not going to read that. This is a very, very fast review of the scientific method. For this scientific method, you may, well, you observe something. In this case, we are dealing about performance. The performance is bad. Okay? Then you try to reproduce that the performance is bad in similar conditions. Okay? You say, a guess, an educated guess, the performance is bad due to the database. Okay? Then you do a test in which you are pounding the database, stretching the database, focusing on the database. This can be as simple as simply create performance indicators for the database. This is the first thing that I will do. If my suspicion is that the database layer, the data tier can be the problem, well, I'm going to put some performance counters and look at them. I see that the performance counters are bad. Okay? My hypothesis has been confirmed. So my model, the database is wrong, has been confirmed. Now I can elaborate a little bit more. Which part of the database? Is the data architecture that is bad? Is that there is a lot of pages broken? Is it a configuration problem of the database? You refine your experiment. If it happens that you have said in the beginning, oh, the database is going to be the culprit, and you do your performance counters and all of them are excellent, what that means? Your hypothesis is wrong, you need to change your hypothesis. No surprise here, logical sense. However, you have not wasted your time. Even this negative results is positive. You know that the database is not your problem. You need to focus your attention in your other suspicions, your other guess. Another, some unstated principles of the scientific method that a lot of people forget about it. And one of them is simpler is better. Other thing, a procedure needs to be repeatable. If it's not repeatable, this means that you need to enlarge your model. You need to include more factors that are influencing your computer. You're influencing your system. And well, perhaps I don't know, perhaps the neighbors upstairs, they have a lot of machines that they create a huge electromagnetic field and it's going to affect your computers. Okay, this is your hypothesis, you need to test it. A model should not introduce more questions than it answers. Okay, I can create a model saying that my performance problems are caused by a little dwarf that live in the machine. It's a hypothesis. However, how many questions create the hypothesis? How the dwarf is able to eat and drink? Who has put the dwarf there? When he's on holidays, why are I still not serving? Has a substitute? Then I have two dwarfs. It's a hypothesis, but it complicates a lot the explanation. As a rule of thumb, a good model, hypotheses and models and explanations are always evolutionary. This means that a newer model may explain more things than the previous one. Doesn't mean that the previous one is wrong. It's simply a particular case. The greatest example that everybody will know will be the theory of the gravitation and relativity. What does it mean? This theory took all the Newtonian theories, 300 years of scientific development, and throw it to the wind? No. Newtonian gravitation